Hi, welcome to my workshop on establishing a productive machine learning workflow for Hack the North 2021, aka how to stop losing your best results. This workshop is motivated by the fact that as machine learning and data science projects go on, eventually code evolves, your ideas evolve, and old code breaks, and you can't reproduce the results that you once had, which makes you lose a lot of time and productivity. And hopefully, through some of these practices, we'll be able to prevent that. You can see on the bottom right below, here's the link to the slides, and here's a link to the completed code from all the demos in this workshop. So I'm Nick. I'm a stats and computer science student here at the University of Waterloo, and I've done internships in data science, ML research engineering, ML research, and ML engineering, so all things machine learning and data science. Please feel free to reach out to me later to talk more about what I've done in the industry. You can follow me on Twitter at Nick Vadivelu, or email me if you have any further questions, or find me on Discord through the Hack the North channels. So who's this workshop for? This workshop is for an aspiring data scientist or ML researcher working on an algorithm, a model, or a method on some data. So super broad class of people working on problems. And essentially, it's someone who's interested in investing some one-time effort to make their projects run more smoothly and to make sure that, things stay clean, things stay working, and things stay reproducible so that as your project goes on, you can continue to evolve on your ideas and compare them to old ideas as well. And really, this is targeted at me 2 years ago, or maybe that's even being generous. It's probably me 6 months ago, because I think some of these ideas and practices are things that would be beneficial in the beginning, as well as for someone who's an intermediate or someone who's more advanced. So the prerequisites for this workshop is I expect everyone's completed at least one small Python data science project before. And so this is not really a hard requirement. We won't do anything too advanced in Python, but I think you'll appreciate these ideas and understand why they're important a little bit more if you have a little bit of hands-on experience with Python, but I'll try my best to explain everything as we go. In terms of all the code examples and the commands that I'll be giving you, these will work on any Linux-based system. So whether it's Linux or Windows Linux subsystem, which is basically Linux that runs within Windows. I highly recommend this over any PowerShell or anything like that in Windows, because honestly, Python's a pain and things like that. This will also work on OS X, but I actually haven't tested it on that because I don't have access to a Mac, but hopefully it'll work there too. And before we get going, we'll talk about what this workshop isn't, so you can leave now if this is not interesting to you. But I'm not going to be talking about how to conduct data science analysis. I'm not going to be talking about making a productive workflow on analyzing data and collecting results. That's not the focus of this workshop. And we won't talk about maintaining models in production. I think that's a whole different topic and kind of out of the scope of this workshop. This is really more for research and data sciencey projects. We won't talk about collaborating with large teams on projects. This is really more for individual or a few people working together. There are obviously a different set of tools that are useful to keep large teams productive. And this won't be about managing a purely analytical project. By purely analytical, I mean really just visualization based and just getting those statistical results, doing statistical tests. I think there needs to be a significant code portion of your project for this workshop to be useful. And I think this is very common in modern machine learning workflows anyway. So here's the agenda for today. We will first be talking about Python environments and how to isolate your dependencies and make sure you have a reproducible environment so others can run your code and so you can run your code on new clones. We'll be talking about testing, which is kind of people have a really bad perception of this in data science, but I promise it can be pain-free and actually save you time in the long run. We'll also talk about static analysis tools. These are tools that will be able to check your code before you actually run it, which you may expect is super useful in Python, which is a highly dynamic language, no compiling, and so errors are only caught when that bit of code is run, which is really a pain when you have a long training script and at the very end you're trying to save and you misspell a variable and then nothing gets saved, and that's like 2 days of work wasted or 2 days of training wasted. We'll talk a little bit about version control tips. I won't be talking about how to use Git, but I'll be talking about some things that'll help you around Git, like continuous integration or pre-commit. Also seems like very software engineering things, but can be very useful for data science. And finally, the section I'm most excited for at least is configuration. And we'll be talking about a library called Hydra and how you can configure your projects in a cleaner, more composable way without having these long argument lists or long configs that are just grow and grow over time and are hard to maintain. Since this is a recorded session, we'll go through all of these in order, but for the actual workshop, we can actually mix and match these sections and go in any order we'd like and emphasize sections that the audience feels is more relevant. So feel free to skip around this video because each of these sections is relatively modular. And a big disclaimer is that this is just stuff that works for me. I wouldn't say this is an established, written in stone workflow that works for everyone. This is just something that I developed over time over my various personal projects and internships. And so if you have other ideas or reasons why the things I suggest may not be good, please speak up, because I will learn something and everyone else will learn something. Or come talk to me after, and I'd love to have a discussion, because maybe kind of selfish for hosting this workshop. I'd love to also learn about what you guys do. Cool. So first we'll start off with Python environments. We'll talk about why we use them. We'll talk about some different types of environments, including pip, conda, Docker, and some others. And we'll end off with a quick demo. So what is a Python environment? Conventionally in Python, the most common way to install packages is using something called pip. And for example, here I have this line on the slide. It's pip install TensorFlow right here. And so this would install the package TensorFlow to your global installation. And so you'll be able to use it in any Python interpreter you spin up. So this is problematic. It can cause conflicts between projects. So for example, if one project depends on one version versus another, that will cause a conflict and you won't be able to run both projects on your workstation. And it's a little more subtle than that. Even if you use the latest version of all your libraries, sometimes libraries both have a common dependency. For example, many libraries may depend on NumPy, but they may depend on different versions of NumPy. So you may have some unexpected conflict that you didn't incur directly. It also makes it hard for others to run your code. If you just have some global installation with a whole soup of dependencies, it can make it very hard for others to run your code, or for you to run your code on a different machine. And thus it makes it hard to reproduce results. Really, you want an isolated environment for each project so that it's easy to get up and running on any new machine and up and running in the future when your state of your machine changes. Really, when I say you want other people to run your code, you may think, well, no one else is going to run my code, it's just me. But trust me, you in 6 months is going to be a completely different person because your workstation is going to have a completely different setup. It's going to be impossible to run things without an isolated environment. So we'll do a quick comparison of two of the major Python environments, Python environment managers that are out there. The first one is by pip and the second one is by conda. So pip is the Python package manager, and essentially it only isolates Python dependencies. Whereas conda is a more general package manager. It's actually older than pip and isolates all dependencies. So both Python and other dependencies, like for example, C++ libraries. And this could be useful in data science. So for example, your code may contain R, it may contain Julia. Your Python libraries may use C++ libraries. For example, NumPy can optionally use OpenBLAS or Intel MKL, which are kind of backends for running these low-level commands. And so conda can actually isolate all of those dependencies. Generally, packages on pips are more up to date because it is the more popular option today for Python, whereas conda tends to have things that are a little bit more out of date. But this is not really a problem because you can actually just use pip within conda environments, no problem. In general, I tend to stick with pip because I mostly work with Python dependencies, and any C++ dependencies I have are just kind of packaged into the Python wheel. But anytime I do have to depend on C++ or Julia or R code, I tend to go for conda. I think both of them have a very similar interface and they're both really easy to use. One thing I will say, if you're using Windows without the Linux subsystem, I would definitely go with conda because conda can also manage your Python installation and it makes it easier to run on Windows. So to be honest, I wouldn't recommend running Python on Windows. At least in my experience, it's been a pain. Maybe that's changed. There are also a lot of other options for managing dependencies and isolating your environment. I think the most common one is Docker. And so Docker, it essentially containerizes your entire workflow. And so you have essentially an entire copy of the OS that's running on top of whatever machine you're running. I won't go into detail. That's a really bad explanation of what Docker is. But on a high level, it's kind of extra for your research-based or data science-based project. I think the workflow is harder to set up. It's harder to get it running efficiently, and it's harder to integrate into your editor. But if you're at a company or if you have experience setting Docker up, I think it's really an excellent tool as long as you have the tooling to make it run efficiently. The only problem is conventionally other data scientists or other researchers may not have the same tooling you do, and so it may be more difficult for them to run your projects than if you just simply use pip or conda. pipenv and poetry are both ways to manage Python dependencies, and they're just slightly more elegant abstractions on top of pip. But to be honest, these are not things that I find particularly useful for data science or research workflows. I think they're much more suited to conventional software engineering applications. They are good at what they do, but I think they're just restrictive and a little bit more than what you need for your research project. Cool. So here's the basic primer on what we're going to go through in our demo of creating pip environments. And so I'm using Python 3.8 throughout all of my demos, but this should work for anything Python 3.6 or greater. So 3.6, 3.7, 3.8, 3.9. So essentially the first line creates a Python environment. And so typically when you use the -m flag, you're running a module as a script. And so it should have a .main. That's just a detail. You don't really have to worry about that. But essentially this will create a virtual environment with a name .env. .env is a very common name for virtual environments. Many editors like VS Code will recognize .env as a virtual environment and actually use that to run your code. But this is just a conventional name. You can really name this anything. Then you use the source. You actually source the activate file in order to activate the environment. And then you're inside the Python environment. You can work with Python as normal. So you can pip install dependencies. You can use Python to open a REPL with open a REPL, and this will have all the dependencies you installed. And if you want to freeze all the dependencies that you used, you can just use the pip freeze command. And essentially this prints out a list of all the dependencies and the exact version that you used. And so if you use the command below, pip install -r, in a fresh environment, this will install all the Python dependencies you had in the exact same way as you originally had them. So this is what makes it so reproducible. Cool. Now we will go into a demo. And so basically in this demo, we will be setting up our project. So creating a Git repo and then actually seeing how pip works. And for the demos in this workshop, I try not to kind of set them up nicely. I try to do them from scratch so people can follow along. At least I find that a lot of demos kind of do a lot of setup steps, but the setup steps are the most buggy prone. And so it's hard to get going. So let's actually go to GitHub and figure this out. Oh, and let me hide my bookmarks bar. Oh, okay, cool. Let's make a new repo. Template, you don't have to use a template. Let's do hack the north demo test. I'm just gonna name it that. Description, we don't need a description. Let's make it public. Add a readme. For the get ignore, I think the Python template is really good and I would highly recommend using it every time. This ignores a lot of the PyCache files that are super useful. For licenses, so this is something you may actually want to consider if you're working on a personal project that you want others to be able to use. I would recommend using the MIT license. I won't go into too much detail about licenses. You can definitely talk to me about it after, but if you would like other researchers to build on your code, and these researchers are affiliated with some kind of institution, typically they won't be able to use any code unless it has a license on it. And the MIT license is probably the most suited for these kind of open source projects. So let's just create this repo. Nice. And then we can just clone this. I'm going to pop open a little terminal here. And then, oh, you may not be able to see this. Let me zoom in a bit. Full screen. Okay, I will zoom in afterward. Okay, clone. Boom, we cloned it. And let me just open up a VS Code inside of this. So my editor of choice is Visual Studio Code. I think it's a good choice for anything, to be honest. It's really great. We open up this folder. Cool. Now we're here. Hopefully this is zoomed in. You can see what's going on. And so on the left here, I have all the files in this repo. And I'm just typing into a little terminal. You can see that I'm using a terminal called Fish. Of course, if you're using Bash or using Z shell, all the commands should just work. There is some differences and I will point them out when they come. But I use Fish because autocomplete is pretty great. Cool. So I have a Python 3.0 installation. As you can see, I can't import NumPy, for example. It's not installed. So I'll create my virtual environment. Cool, and then we'll activate our virtual environment. So in the slides, I told you that this is the command you need. Since I'm using a shell called Fish, there's actually a .fish file. Don't worry about the differences, but you most likely want to run this one. And cool, in our environment, we can do things like pip install NumPy. And as you can see, I have a cached version, but yours will probably take some time to download. And then you can just run Python here, and we're in our 3.8 interpreter. And ta-da, it works. We can make an array, for example. Cool. And now we want to actually freeze our dependencies. So let me actually install one more thing just to show you. pip install Jupyter. Jupyter has a lot more transitive dependencies. As you can see, there's a ton of other stuff that needs to be installed. Cool. And then you can actually just pip freeze this into requirements. Oh, that's not what I wanted to do. Requirements.txt. As you can see, my autocomplete is really helping me out here. Awesome. And so here you can see all the dependencies we have and the exact versions of all these dependencies. And this is something you would include in your GitHub repo and commit as normal. And of course, if you want to install everything in this, you can do -r requirements.txt. And since we have everything, nothing's going to happen since the requirements are already satisfied. But if you created a fresh environment, this is what it would do. You can also manually specify the requirements.txt and just create this file on your own. So for example, let's requirements. I'm going to call it requirements.in, and we'll see why I'm using that name later. But we can specify, for example, NumPy or Jupyter or whatnot. We can specify that it should be greater than some version, or we can specify that greater than or equal to some version, precisely some version, between two version numbers, whatever it may be. And then you can of course pip install -r requirements.in, and that'll work just fine. Cool. That concludes our little Python environment demo. And so essentially you should be working in this environment all the time. This is kind of a convenient way to isolate your dependencies. So one issue with what I just showed you is kind of that huge requirements.txt file that I showed you. We only installed two things, which was NumPy and Jupyter, but we have a whole bunch of dependencies on our requirements.txt, which is hard to understand and hard to manage because we have no idea where these dependencies came from. It's hard to individually upgrade these dependencies over time. This may not be problematic for a short data science project, but maybe if you're using something again in the future, you have no idea what to upgrade and what not to upgrade. And so a nice solution for this is something called pip tools. And so essentially in pip tools, you create something called a requirements.in with the libraries you want. So exactly the file I created at the end of that little demo there. Then using the requirements.in, you use pip compile to actually create the requirements.txt. And this is really nice because, and then you can synchronize your environment to the requirements.txt using pip sync. So this is really nice because you have what you want or what you intended to install in your requirements.in, and then you have what your actual dependencies are in your requirements.txt, and kind of separating those two things so it's easy to understand what your project actually wants versus what your project actually has. Also, pip compile has some really nice formatting, so it can tell you exactly what package required this package. So for example, if you install Jupyter and it requires like the Qt console, for example, the file will have an annotation that says, okay, Qt console actually comes from the Jupyter package. So it's quite nice. This is something that I'm starting to use more and more, not something I have too much experience with, but I definitely have a positive experience so far. And some other little tips. So as I mentioned, things like VS Code can recognize the .m directory in your project. And setting that up is pretty simple. You can just look at the Python extension for VS Code. Also, it's kind of useful to consider making your project a mini package. And so people can just pip install git plus your project. That's kind of out of the scope for this workshop, but it's pretty easy to do. You just make a file called setup.py, and then you can use setup tools and follow the tutorial on the Python site. But this makes it really easy to reuse your code without copy and pasting stuff everywhere. But this is, again, for a project that's open source and something a little more reusable than just a pure researchy project. So here you can, I guess, pause for questions, but this is a recording, so we'll keep it going. So next topic is testing. And kind of the motto is, please don't make me do this. This is what all data scientists and researchers say for testing. It's like, oh, why do I need testing? I'm not an engineer. But hopefully I'll convince you that this can make you more productive. So yeah, the common argument is why test? I am not a SWE. And I promise there are reasons to test. And so first thing is that there's assurance that things work. So really, you have no idea what your code is doing unless you have some input that you give it and it gives you some output and you verify that output against your expectation. That's the definition of a test, right? So you have no assurance that things are working unless you test it at least once, whether this is during development or afterward. You need some way of knowing they work. Tests also serve as live documentation demonstrating how things should be used. So, after some time of not using a certain piece of code, you may not be completely familiar with inputs, outputs, or exactly what a function does. And doc strings are helpful, but often doc strings go out of date because the code evolves, especially for a research project. Code evolves very quickly and inputs and outputs may change. And so it's really useful to have a test that runs periodically so you know it's always up to date, kind of demonstrating how things should work. And it also makes refactoring possible. And I emphasize possible because without a test, you have no assurance that things continue to work once you change them. They may have worked the first time you created it, but if you're refactoring or changing things or adding new features, you have no idea if things are still working unless you have some way of verifying it. And I hope to convince you that having a test is a more efficient way to do so than simply running all your functions and kind of checking outputs and being like, okay, yeah, this sort of looks right. The cons are it takes up time that you could have used to develop new things. And this is definitely true. Like in the time that you wrote tests, you could have implemented a new feature. But hopefully through my demo, I'll convince you that really the time is negligible because the test kind of comes from how you develop the feature, especially for data science, because we're not testing every corner case. We're not validating inputs, for example. We're not, as a data scientist, we're expecting to use our function locally in our project. And so we are kind of have expectations on ourselves on how we use it. And so our tests look very different than for someone who's writing tests for users that are not themselves. And another con is with fast evolving research code, tests grow stale, and so they must be changed often. This is kind of true and false. This is true when you write gigantic functions that do everything. And so every time you add a little feature, you have to change the whole function. And I think this is counterproductive anyway. But if you're writing small functions that each have a little feature, so maybe you want to test out different loss functions, if you have many different loss functions that do different things that kind of have the same interface, I would argue that you don't need to change tests too much at all. And if you do, then you're already working in a counterproductive way as opposed to a way where you can build on your research and build on your projects. So before we dive into the code, we're going to be looking at a larger example now. And this is going to be the running example for the rest of the workshop. So essentially, we are training a simple neural network on the fashion MNIST dataset. So you may have heard of MNIST. Fashion MNIST is very similar, but instead it's 28 by 28 black and white images of clothes. And these clothes are split up into 10 categories. And essentially, we're trying to train a model to predict which category each image belongs to. And so, for example, shoes or a shirt, or I forget the categories, but you get the idea. For neural networks, you may be familiar with frameworks like TensorFlow or PyTorch. And for that exact reason, I'm using a framework you may not be familiar with because that's not the important part of the code at all. I'm using JAX and Flex, which right now are my two favorite neural network building libraries. So JAX is a library like NumPy, but essentially it provides automatic differentiation and runs on accelerators like GPUs or TPUs. It's really a pleasure to use. And Flex is an abstraction built on top of that for writing neural network code. Through this project, this is not a large project by any means, but it's definitely not a tiny toy example because we are going to be demonstrating things like learning rate schedules and tuning hyperparameters. And so something sort of realistic. I wouldn't really claim it's too realistic, but it's sort of realistic for sure. Cool. And so we'll go over how to test. And so we'll have a little bit more setup to do as well. So I'm actually going to delete these two files because we're going to copy in some other files. And so I'm going to copy in a bunch of stuff from HTN. Nope, that's not what I want. Yeah, I'm using my little cheat directory. And then let's say .source. Copy it in. Let's copy in here. Cool. And so we have all of our source files, and actually let me go in and delete those tests right now. cd source tests. So we'll copy in the rest of the rm rf tests. Cool. And then we'll also have to copy in our requirements.in. Actually, requirements.txt. Well, let's actually copy in our requirements.in as well. That'll make it helpful. Cool. And so we can see here that I define a requirements.in. We'll use a bunch of these later on during the workshop, but the primary ones you should be concerned about are these top ones here, and actually some of these other ones, but we'll get into that later. These are the dependencies that we actually wanted in our project, and then these are the dependencies that were generated through all these. So as you can see, there's tons and tons of dependencies here, and this is much easier to read. So let's set up our environment. Like I mentioned, pip install -r requirements.txt. And so this will get our environment up to speed with what we're working with. And while that's running, let's take a quick exploration of the code. And so don't worry about most for now, but we can just look at this main file here. Cool. Thank you. So in this file, essentially, it's pretty simple. We have a training step that we define. We have an evaluation step, and essentially we have a training loop where we are doing a bunch of train steps. I think this is pretty standard code. You can take a look at it in more detail later, but we'll be focusing on developing a new feature for this. So essentially we have this loss function called cross entropy loss. And we are interested in adding new functionality to this loss function because we want to test out a new research idea. And so we'll see how we can do that efficiently because we have tests, and how we can add a new test for that. So I hope this is almost done. Oh, cool. Nice. Good timing. So let's actually let's see how we can add the tests in. So right now I have this source structure where we have our src folder, which has all of our source files. And for the Python testing framework I'm going to show you, PyTest, you can optionally put your tests either outside the source or inside the source directory. I prefer inside, just because it makes it a little bit easier to orchestrate things. So in here, let's make our first test, and we're going to call it test main.py. And the reason we're going to call it test main, that's a common convention to prepend like test to whatever file you're testing. And right now we're going to be testing main, and we're going to be testing this loss function. So I'm going to pretend that we already had this test here, and then we're going to add a new test afterward. And that's the kind of the whole theme of the rest of this demo. And so here we can import PyTest and import jax.numpy as JNP, which is our one dependency here, which is essentially a NumPy-like API from Jax. Cool. And so how do we actually run these tests? So pretend this already existed. And the way we would run these tests, so let me just cd into the source directory. You can run python-m pytest vvv. This will basically find all the test files, and this will find any function that's named like within these test files that's prepended with this test name. So for example, test_loss, that's has a test underscore to start. We can just run it here. Oh, and it failed. Why did it fail? Oh, okay, no wonder, I forgot to import it. Cool. And nice, we have our first passing test. Again, this is kind of cheating because we use a test we already had, but this is kind of how it looks like. You run Python. First we'll look at a failing test. So we run python-m pytest, and then this vvv basically gives us verbose output so we can see more details about what's going on. It said that it ran this test and this test failed. Typically it would run all your tests and collect whether they failed or passed. We can see very specifically what the error was. And so here the name wasn't defined, which we forgot to import it. And this is how it looks when things pass. And so it collected one item, it ran it, it passed. I always feel nice when I see green text on my screen. Cool. So now we're interested in developing a new feature, which is like what I called label smoothing. And here is the workflow that I would recommend for doing this. And so first I would literally just copy this test, and then let's close this. Yep, don't save. Cool. And so I generally develop new features or new functionality for my research code in something called Jupyter Notebooks. And so Jupyter Notebooks, if you're not aware, is a collaborative, it's not a collaborative, an interactive environment where you can have code, plots, markdown, et cetera, et cetera. And right now I'm using something called Colab, which is a online version of Jupyter Notebooks. And the nice advantages of this is that you can optionally choose an accelerator for the backend that'll help you run machine learning code more quickly. So for example, my PC right now doesn't have any GPU, but I can use a GPU for free on Colab. Typically, if you have like complicated requirements, I would highly recommend just running Jupyter locally, but for the purposes of this workshop, I'll just run it here because I know everything's available on Jupyter Notebooks. So let's import Jax and import jax.numpy as JNP. And oh, I forgot to explain this, but this pytest.approx basically lets you have like a plus or minus band around the number that you expect to be produced by this result here. And so we said that we wanted to assert that this loss function's output was approximately this value, plus or minus 0.01. And this is, of course, pretty important for numerical code because, you know, there's floating point error. And honestly, 0.01 is really, really generous. You probably want to do something more like 1 to the negative 1e to the negative 8. But the reason is I truncated this output here, so I thought, you know what, let's just give it a generous bound. It's not too important. Cool. Anyway, so to start out, and let's also copy in the function we're trying to modify, which is this one right here, this get cross entropy. No, can I not copy? Yes, I can copy. Cool. And so let's make sure this runs. Check shapes is dot define. All right, yeah. So I will talk about that library after, but we actually don't need it right now. PyTest not defined. Yes, I'm sorry, it is not. Doop. Cool. So we can see that we are getting the right result here, and we want to add a new feature. And so label smoothing, I won't explain the actual math behind it, but on a high level here, let me actually I can explain this step by step. Let's do this. So let's actually show this code here, and I'm going to say that well, this is kind of how I develop code. I just put everything into a notebook and make all the variables globals, and then we can kind of see what's going on from step by step. So we know it's true. We can just simplify this a little bit. Cool. So right now we first do a log softmax, and so this essentially turns our logits into the log of some normalized probability distribution. You don't have to really worry about what that is precisely. So next, we actually want to get our predictions out. And so here you can see that this is something called a one-hot encoding. Once again, don't worry if you are not too familiar with what that is. And so essentially in this one-hot encoding, let me just show you what the labels are like. So these labels are just indices into the label. So for example, this is the 0th category, this is the 2nd category. And then when we turn it to one hot, you can see that it's 1 on the 0th index and 1 on the second, the 2th index, I suppose. And essentially we're trying to penalize this. We want this model to predict this as closely as possible. And when we do label smoothing, essentially we don't want these to be just 1s or 0s. We, for example, want this to be less than 1 or slightly greater than 0. And so we do this through something called a label smooth parameter. And so let me actually kind of go through the workflow, how I might develop this. So here, so I know I want to alter this. And so let's say smooth labels, and then here. So we don't have that defined. Let's take a look at how smooth labels looks. Okay, 0, 1. So really I want the ones that are 1 to be slightly less than 1, or the 0s to be slightly greater than 0 by this like label smooth amount. And so let me just define that up here. So equals 0.1. And so then I want basically, I want it to be about 0.9 whenever the array is equal to 1. So let's do smooth labels equals 1. And then I want it to be 0.1 whenever it's equal to 0. So let's actually do that. Oh, that is not, oh yeah, it's still smooth amount. This is not the most efficient way to implement it, by the way. And this is just a kind of a naive implementation. So we kind of see that this works. And then we can kind of verify this here. Nope, we want to reassign smooth labels here. Cool. So we have a slightly different result, and in real life, I would verify that, you know, this is actually producing the result that I want. And so by doing some math and making sure that it's actually the right result. And so let's redefine our function, kind of like we did. So paste this here, pretend the code formatting is not awful. Oh, forgot the last line as well. So this is not the smoothest way to develop a feature, but this is kind of how the workflow goes. And nice. And so we can kind of verify that once again. Let's kind of copy and paste some of this code that we did. And then let's add a label smooth amount equals 0.1. Remove that from here. Actually, by default, we want it to be 0. So, and then so here, boom, once again, we know this is what it was supposed to be. And then when label smooth amount is a little bit more, now equals 0. Let's say 1, for example, boom, we know we wanted some different value here. And so, of course, we would have verified this mathematically by actually going through the math, but here this is just a workshop. So let's pretend that I have the ability to just know if it's correct or not right away. And now this is our test. The way we developed our feature, the numbers we use is the only test we need. We just need to make sure that things continue to work. And so over here, I would just define a new test function, test smooth loss. Actually, it should be smoothed. And then we have the test that we ran in our Jupyter notebook, and then we run PyTest once again, and hopefully this will pass. Oh no, label smooth. Oh yeah, of course we forgot to actually paste in the code. And this may seem like a rare issue, but this is something that happens all the time where I develop something and then I forget to paste it in. Like, tests catch this stuff. And ta-da, it worked. And that is all I am asking you to do, is while you're developing your feature, kind of get a sense of what you're doing. And then once you have this feature, just the simplest test. This is not catching any edge cases. This is not, extensively testing your function, but it'll just make sure that your function continues to work over time. For example, this is definitely not the best way to do this. I would actually do this a different way, which is using something called jmp.where, and then wherever the smooth labels is equal to 1, I would use 1 minus label smooth amount. And otherwise, I would use label smooth amount. Right. This is like a much slightly more efficient implementation, or I think it compiles down to the same thing, but it's actually, let's pretend it's a more efficient. And then I can actually verify that, okay, this is still working. Cool. Things are still running. Another nice benefit of this is we know that any old uses of our loss function are still functioning. We didn't have to create a completely new loss function called smooth cross entropy, which we may have done if we didn't have any tests, because we're like, oh, we want our old things to continue to run the same way as they ran before. But now we have some assurance that indeed they are running the same way as before because we have this test here. So it allows you to keep your code just much simpler. And I hope this is convincing that it really didn't take much time at all. Like, we just copied in the code that we used during development. Let me copy in the rest of the tests and kind of show you some other examples of good tests to have in your machine learning workflow. Source tests, and then we'll paste them here, -r. Cool. Let's take a look at some of these other tests. And so as you can see, I have one test file per normal file I have, and I'll just briefly skim over ideas for other kinds of tests. We won't look at this file. This is not too helpful. So here, you can see that I'm also testing accuracy. One other thing that's also super helpful is to just run your main file with really simple defaults. And so you don't have to worry about this code. We'll talk about this a little bit later. But essentially, I'm just specifying that we're going to use a couple of steps. The batch size is going to be tiny. The validation batch size is going to be tiny. We have this like little test mode, which prevents like just saving random output. And we just have a couple of evaluations and a couple of reporting steps. And we just basically run our main through. And when I say this runs slowly, this doesn't run that slowly, but it's slower than the rest of the test. And I'll explain why I marked this way a little bit later. But this basically gives us assurance that any code that we have, at least our main runs top to bottom. And this is super, super helpful because, when you're actually running a training script that has like maybe thousands and thousands of steps with huge batch sizes, which takes like maybe hours or even days to run, you don't want it to fail at the very end. And so just having a really tiny run example so that the whole code runs through once just to make sure that it works is, in my view, invaluable. And so let me actually make sure these tests still run. It would be really embarrassing if nothing worked. Okay, things are passing, which is, I guess, good to know. See, this main takes a little bit longer because we're running our entire training script with a super tiny, didn't take as long as I expected. It just ran everything top to bottom, which I'll show you a little bit later. Testing models. So for example, I'm just literally creating this model, initializing it, and then doing just a forward pass through it, and just making sure things run without errors, because sometimes you insert breakpoints or things like that into your code that you're not expecting. And so just making sure things run before you launch a job or schedule things. Another options for learning rate schedules. Literally here, you may not wonder where these numbers come from. I will show you. So learning rate schedules are essentially a way to alter your learning rate over time. And one useful way, and you should definitely test these and see how they're going. And so you may think, well, it's such a pain. How am I supposed to test the actual numerical outputs? I will show you how I developed that literally for this workshop. And so, I was in the process of workshopping these numbers, and I just visualized how the shape looked. It's like, okay, this looks approximately right to my eye. So I literally just printed out these values and then pasted them here, and it was that easy. You may be wondering, well, you're not really doing any verification. What's the point of this? Your function output is equal to your function output. Yeah, this is true. But once you add slightly new features to your function, or if you change your function slightly because of a new research idea, you'll want this test to make sure things are still running the way they were. Another option for these is to literally re-implement these in a different way. And so this exponential decay is implemented in a slightly more complex and efficient way. But just by doing the naive thing here, you can verify that your more complex algorithm matches what you expect here. And you don't have to worry about the details, but you can see all these examples in the updated repo. And for test data, this is one I wanted to talk more about. So I have this data augmentation called eraser. And so we can actually pop this into a Jupyter notebook and see how that looks. Oh, let's copy this. So this is something that's a little bit harder to test. Let's go to the scratch pad. Let's go to the bottom. That new code cell, and then we have to matplotlib, if you don't know, is a visualization library, but hopefully you should know that. And then let's actually copy in the. So as you can see, I'm doing a really inefficient thing, which is copying this code into a notebook, which I would not recommend. I would actually recommend spinning up Jupyter notebooks right here and just importing things directly. The reason I'm not doing that is just, what is happening? Is for the purposes of this workshop, things just work a little bit better on Colab. Okay, there we go. Cool, and then blah, blah, blah. Here, and then, no, it changes things in place actually, so I should do image here, I think. So this should work. Okay, I'm not sure why this is working, but essentially it will erase a random party, but this is actually a good reason to run tests and actually check what's going on. But essentially this should have kind of erase part of this picture, but it's kind of randomized. So it's very hard to test that exactly the right thing is going on. And so this is why I have this test here. And I'm super glad in this example, you saw things actually broke. So I should actually double check why it's not working. But essentially here, this is just making sure the code runs from top to bottom, but it's not actually testing anything. It's not asserting that the output is correct. It's just making sure it runs top to bottom. And the reason this exists is so I can copy and paste it into a Colab and actually debug what's going on. Or if I change that function, see if it's still working properly. There is something called property-based testing, or I guess property-based testing means something else, but it's also it's an overloaded term for data science as well, where instead of testing something precise action, you can test properties. So for example, if you expect to erase 20% of the image, you can test that, the statistics of this image changed by some fraction that you can compute. I find this is a bit too complex for my code and it requires a bit too much thinking. I instead just like to have code like this, just making sure it runs top to bottom. And then when I actually change the function, I can just paste this into a Colab and make sure things are working correctly. I would not say this is ideal by any stretch of the imagination, but it's something that works. Cool. That is all I had to say about testing. Let's get back to the presentation. So hopefully I've shown you some useful data science tests, and I've shown you that it really takes no time at all. It should be a part of your development process. And so some examples of things I already showed you is inference on your model, just making sure that you can run an example through without any errors, because, in Python land, you can have a small misspell somewhere in your model and you'd have no idea until way too late after you launch your job on your cluster or whatnot. Testing learning rate schedules, making sure they're working correctly. Verifying examples of your data, just maybe loading a batch or loading a single example and just making sure the dimensions, the mean, standard deviation kind of looks like what you expect. This is super useful because, for example, if you're working with live data that changes over time, you might want to kind of understand distributions about that data. Or if your pipeline changes, you may want to make sure those things still work. The next is just making sure that configurations still kind of run. And so I'll show you a little bit more about configuring your projects later, but as your project evolves, you'll have different configurations and different ways of doing things, and you want to make sure that your old things still run so you can compare results, reproduce results, etc. In this demo, I showed you PyTest, which is my favorite framework for testing because it's so simple. You saw there's no boilerplate. You just make some files, make some methods called that begin with test, and it'll run everything for you and give you a really nice UI. Unit test is an object-oriented framework that's included in the standard Python standard library. And there are many specializations that exist for machine learning, such as tf.test, which is from TensorFlow, and checks, which is for JAX. It's definitely not my preference in terms of the user interface and how things are set up, but it's also a great option. It's solid, works really well, and it's good to know because there are specializations of it available. Excuse me. Cool. So that concludes testing. I'm hoping I convinced you it's super easy and it's super helpful to keep you confident that your code is at least working like it once did. Correct is a very strong word to use, but working like it once did. And next we'll talk about static analysis, which is kind of making sure your code works before it even runs. And we'll kind of answer the questions of, is it even worth the trouble? Because there is some setup trouble, right? We'll talk a little bit about linting and type hints and type checking. So what is static analysis? Static analysis are a set of tools to analyze your code before it's run in order to catch errors. And so you can imagine that analyzing code before it runs is really effective for compiled languages like C++ or Java or Swift, but it's less effective for dynamic languages like Python. And when I say dynamic, I mean languages that are not compiled and you won't run into errors until you reach that line of code. And so, they're less effective, but they still are very useful. And so they can give, and static analysis tools also, they can give many suggestions on code style or code complexity. So the question is it worth it for a data scientist? Like, you can imagine if these analysis tools are giving you suggestions on style, like that's a kind of a waste of time. As a data scientist, your product is not the code you're writing. The product is the analysis or the results of the code. And so you're not trying to have some perfect, clean, amazing code. And so these false or these like noisy signals can just waste your time. False positives also waste your time. I told you that these analysis tools are not perfect for Python. And so if these are giving you erroneous messages or flagging issues that are not actually issues, again, these are wasting your time. And the whole point of this workshop is we want to find ways not to waste our time. And once again, this whole idea of a low signal to noise ratio, especially for data science code, maybe something is a code smell or maybe something is suspicious for software engineering code. But when we're writing research code all the time, we're using little hacks or little ways to make our code a little bit simpler or faster or whatnot. And so these tools may flag things that we don't actually want to fix. And that's annoying. And that's not, that's definitely counterproductive. But again, there is nothing more annoying than running a day-long training job that just fails to save your checkpoint at the very end because you misspelled a variable. You really want to catch those in advance. So I'm going to say that a static analysis tool PyFlakes is really a lifesaver. And I have a quote here from their documentation, and it's that PyFlakes makes a simple promise. It will never complain about style, and it will try very, very hard never to omit false positives. So this means that it will literally only show you when you have errors in your code. And if it's not sure if something is an error, it just will shut up about it because, often these false positives can pop up in Python code that are annoying. And I think this is like perfect for data science because really you just want to catch these errors before you run your code. You don't really care about style unless you are kind of working in a production environment, but really for your own researchy project, you're not so concerned about style. You just want to know when there's problems. There are also other popular linters that I'll mention that are not so suitable for data science, but are still excellent options. One is PyLint. This is a very opinionated linter that enforces really good coding habits. And this is very popular. It's used at companies like Google. I would say, again, this is even if you're writing code intentionally to be as clean and as with good practices, PyLint will usually give you something to fix. And so again, it's a kind of a time waster for data science code. Flake8 is another popular linter, and it's very popular among open source projects. And so it's slightly less opinionated than PyLint, but still gives you some suggestions. And actually, it includes PyFlakes as it's kind of a superset of PyFlakes because it uses PyFlakes and a bunch of other tools in order to do analysis on your code. This is my personal favorite because I guess my preference is to just kind of have cleaner code in my projects, but it's definitely maybe not so suitable for data science because it does complain about things you may not care about. And most of these editors have linter integration, so you can kind of see the errors as you edit code, as you save code. Unfortunately, VS Code doesn't support PyFlakes yet, but one little hack is just using Flake8, and then you set the error flag to F, and then that will only show the strongest errors, which is actually the output of PyFlakes, and I'll show you that a little bit after. So that's static analysis on your code, and there's another option in Python you can do this in older versions of Python, but as of 3.6, there's something called type hinting, which is done with this syntax above. And so essentially you can specify what you expect the inputs of these functions should be. So for example, x should be an integer, y can be any type, and z is basically a optional dictionary. So it could be none, it could be dictionary. If it is a dictionary, it's a dictionary from strings to ints. And this doesn't have any runtime effect. Python doesn't check any of these at runtime, but it serves as documentation for the reader so they know what's going on in the function, and it's checked by tools like MyPy or PyType. MyPy is an open source tool by Dropbox. PyType is a open source tool by Google for checking these types. And it's super helpful. It can do things like, for example, if you use Z in your function without checking if it's not none first, MyPy will flag that as an error like, hey, this could be none and you're using it as if it's not none. Maybe you should check if it's none. And so that's really helpful because you don't want to be handling that case incorrectly. But honestly, based on my experience of using these tools for my projects, I think it's more trouble than it's worth with data science projects, because a lot of the time these errors are false positives and you will be working hard to kind of make these tools stop complaining about your code. And these type annotations are super helpful, in my opinion. It's great documentation for the reader, but the actual checking aspect is just too much effort and more effort than it's worth for a data science project. In my view, you may find it helpful. And I kind of grouped code formatting into this bucket of static analysis, but in my experience, this really saves time because nowadays I never think about format. I just write code, however, brackets everywhere, lines way too long, it's super hard to read. And then I just push a button and then it gets automatically formatted into a format that is consistent. It may not be perfect, but at least it's consistent. And so if you're someone who cares about how your code looks, this will help you because you'll no longer be wasting time indenting perfectly. You just write stuff and then it'll be formatted for you. I list 4 popular things here. Black is the most popular code formatter. In my opinion, it spreads out lines a bit too much, so it's not ideal for data science code because ideally things are a little bit more compact, and so you can kind of see the math behind the code very easily. But again, personal opinion, this is definitely the most popular one out there. YAPF, or yet another Python formatter, second most popular, lots of configuration options. It's my personal preference. AutoPep8 is a slightly less opinionated one than the other two. It just makes your code comply with PEP8. Also a great option. iSort is a tool that's kind of orthogonal to the others where it just sorts your inputs into categories. And again, you may not think this is too important, but just having these groups where you know what's in the standard library, you know what's from pip, and you know what's local it just makes it easier to look at code. And I will show you that it's really zero effort after you set these up. And so there's no reason not to use them. Unless you're worried about the extra half a second of CPU time you're using formatting your code, I suppose. So I won't actually show a demo for this directly because we will be going over this in the next section, but it's pretty simple to install all of these. You can just pip install all these libraries, and if you haven't seen the syntax before, you can install multiple libraries from pip by just separating them with spaces. You can run MyPy over your code using MyPy over your source directory, and then this will just emit warnings or outputs with line numbers on your terminal. Same thing with Pyflix. It'll just check things and emit errors on your command line. This is the syntax for YAPF, but it's very similar for Black or for AutoPep8. But basically, you can format the source directory. These are some flags for YAPF that I find useful. Recursive will do all the subdirectories in there as well. In place will actually modify them in place. The other option is not in place, which will actually just show you what changes it would make. In my opinion, it's kind of weird that the default is to do that, but that is what they do. And parallel is it'll process all the files in parallel instead of sequentially. And then iSort will run iSort on directory, sort your imports. I'd recommend running it in this order, running YAPF first and then iSort. But again, we'll automate all of this later, so we don't have to think about it at all. You can configure all of these things generally. So MyPy has a file called mypy.ini. I forgot what it is for Pyflix. YAPF has the .yapf.style, or the other way around. iSort has its own thing. I would recommend just making a setup.config, which we'll actually show in the later slides. Cool. Next, we will talk about version control. And so in particular, we will be talking about pre-commit, we'll be talking about continuous integration, and also the challenge of using notebooks. And so you might think, these things are such software engineering tools. Why do I need these at all? But I'll show you that they're useful because they automate things and make sure you don't have to think about things. And the less you have to think about these like little minute technical details, the more you can focus on your actual problem and your actual algorithms. And so just to be clear, this is not a Git tutorial. I am talking about these tools in particular. So a question I've heard maybe once too often is, do I need version control for machine learning? The answer is yes, please. You don't have to have a clean source tree. You don't have to have perfect commit messages. You don't have to, have really small commits like you would on a software engineering project, but please, 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 please use version control. It will save you, because you will change something, it will break something, and you would want to revisit old code to make sure what's going on, see how projects evolve, understand kind of how features, you want to be able to look at older code and understand where these different codes came from. Branching is not something I use so often in machine learning projects. I find it kind of wastes my time, but you may be someone who uses branching to develop, kind of implement new research ideas. And so please. So what is pre-commit? Pre-commit are actions that run before you commit code. And so these are automated, and these can do things like format files, clean up white space, static analysis, etc. This is really helpful because, I can, more than I can count, I've committed the wrong files or committed the wrong code to a repository. And these little checks can maybe catch things before they go wrong. For example, static analysis may catch that I'm using kind of mismatched files and things won't work properly. And so it'll catch that for me. What shouldn't be in pre-commit? You can pretty much put anything you want in pre-commit. You can have arbitrary functions run before you commit a file. But typically nothing that takes longer than a few seconds should be in pre-commit, because it kind of just wastes your time. For example, tests. Actually, personally, I really like my tests to be in pre-commit because my data science tests are so minimal, and so they're so quick, and so I can just run them really fast before I commit my code just to make sure things work. But that's definitely not a general recommendation. And this sounds kind of extra for data science, but I'll argue that it's helpful, because when you don't, when you can do static analysis on your code to make sure things are correct, when you can just clean up these little things without any effort, I think it's worth it, because when you revisit code in a couple weeks or a couple months, trust me, a couple weeks is enough to forget stuff. Things will be in a state that is easy for you to understand and in a state that actually works. Like you can be confident about it working. And also, it's just satisfying for me to see the green success bar every time I commit. It'll give you a little message I'll show you, and so that's enough for me. So setting up pre-commit is really easy. It's another Python dependency. You just pip install pre-commit, and you set up your pre-commit. You just pre-commit install, which will kind of create a Git hook for you, which will do that. And then you create this file called a pre-commit config.yaml, and we'll show you how this looks in the demo later, which basically specifies the actions that should be run. And you can update these dependencies via auto update, but that's not too important. Before we move on to that demo, we'll briefly talk about continuous integration so we can kind of do both at once. So this is kind of similar to pre-commit, but it's kind of a post-commit kind of thing. So these are processes that are run and checked when triggered. And triggers could be either a pull request or a push to main/master. And for production machine learning workflows, there are really excellent tools like weights and biases, but that's not what I'm going to talk about today. But things like weights and biases via continuous integration can, for example, train your model very quickly and then just verify that the accuracy is above some threshold. Or it can verify the distribution of your data. It follows something that you expect, et cetera, et cetera. Weights and biases is an excellent tool. Not something that I use extensively in my research, but definitely something I want to start using. For personal projects or for small research projects, I just want to make sure that code runs. I want to make sure when I push something that, things are running the way I expect. And so when I next clone my repo, it will just run. And I think this is good insurance, because once again, there are countless times where I just push the wrong files or push broken files because research is research. So this is very helpful. I would say GitHub Actions is the simplest way to set up continuous integration. It's built right into GitHub. There are other alternatives like Circle CI or Travis CI, which require third-party tools, but honestly, GitHub Actions is super brainless, and I'll show you why. Cool, let's do a little demo of how all this stuff works. So we are back in our little repo. Do I have, no, I did not copy. So let me pop this open, nice. And so we will copy over. So here is a step-by-step guide on creating a pre-commit YAML. First, step 1, copy it from your old project. Step 2, you were done. Literally, that's it. Yeah, I literally create this file once and then I copy it into all my new projects. And that's not an exaggeration at all, because there's very little I want to change between them. Cool, so I just copied it to this directory. Let's take a look at how that looks. Oh no, where did I copy it to? Oh, I copied it into source. I did not want it there. I want it down here. Nice. Cool. So this is how a pre-commit YAML looks. So if you're not familiar, YAML is a configuration format, which basically has like dictionaries and lists. Anyway, I won't go into much into that. But essentially there are various hooks that you can install that will run. And so for example, here is one hook that I want to run. This repo, you can get it from the pre-commit website. If you just go to pre-commit, you can see a list of hooks and you can just find this from there. This is the version of the hook. You can also just type main, or you can type master, and then through auto update, it'll populate the version for you. But I'm using this version in particular. And it can run different things. So for example, trailing white space and end of file. So, these are two things that are annoying in diffs for me, because sometimes white space changes and I'll see a diff in a file and it's like, oh, why did that file change? And it's like, turns out that it didn't change. I just added a space by accident. So this is super easy for cleaning that up. I like to format my code before my pre-commit, again, using YAPF, and I could probably add the flags, but it's actually not necessary for this pre-commit hook. Sorting my inputs, again, super easy during pre-commit. And then flake8. So I mentioned that PyFlakes is the recommended linter that I would choose for data science, but actually the pre-commit hook for PyFlakes is broken right now. I don't know why. So I would actually just use flake8 instead. And then instead you can use select equals F, and then this will force only the highest level errors to surface. And this is literally only surfacing PyFlakes errors. And so a little workaround for you, I suppose. In terms of initializing this, you can just do, well, first of all, we can pip install pre-commit. It'll actually already be installed because it was in our requirements, but we do that here. And then we can do pre-commit install. So it'll install this little git hook here. And then we can also do auto update here, and then, everything's already up to date. But for example, if we had revision equals main for any of these, I'm going to cancel this because this can take some time. It'll update that version for you. Cool. So let's actually take a look at how this looks when we actually commit some code. So let's actually commit all of this. Oh yeah, we copy and pasted all this new code. Let me make this formatting awful so you can kind of see what happens. Random spaces. I'm going to reorder some of these. And cool. And so git status. So we haven't committed anything. We have our requirements here that we haven't committed. We have all of our source files, and we also have this pre-commit.yaml. And let me add some stuff to the git ignore. Actually, sorry, this. Okay, yeah, let me add some stuff just so we don't commit anything we don't want to commit. This is Hydra stuff. We'll see this later, but output source dot output. Cool. We'll have some output that we don't want to commit anyway. So we can just add everything. Let me actually get rid of that. Cool. Nice. Cool. So we added a bunch of stuff here. We don't have to worry about all these configs. These are, we'll talk about these a little bit later, but these are a bunch of source files and the pre-commit, etc. All you can commit is, let's say, initial upload. As you can see, I have done this before. And cool, so what is going on here? Nice. So we have our pre-commit stuff. So when trimming white space failed, that means it actually fixed the file. So files are modified by this hook. And so if we just re-add them, they'll be already fixed. Same with this end of file, hook. Files are modified, and a bunch of these are modified. Ooh, I think it formatted in a way that I did not intend. It's okay. That's actually totally fine. So normally I would have something called a setup.config. Let me actually copy it over from the other project. Setup.config, and then this will be right here. Cool. This is a file where you can configure the various aspects of these things. So for example, I'm configuring YAPF with a bunch of my preferences, and I sort with a bunch of these. And whenever you run these tools, it will automatically look to these for to format your files based on this style. Anyway, so as you can see, after YAPF and isort ran, some of our things were fixed. So for example, here, our arguments were all moved to the same line as I normally would expect. Our imports were kind of categorized and sorted as we'd expect. Cool. And then flake8 passed, which is great. So our code doesn't have any weird errors. But for example, if we had, let's say we misnamed this, and then if we ran PyFlakes flake8 whatever on source, see we have undefined name from logits, and that is super helpful because we know that we misspelled something up here. Oh, where am I? There we go. We misspelled something here, so it's a pretty easy fix. Cool. So once things are fixed, you can do git add, and then you can do git commit. One little shortcut is you can git commit -am, and then so A will add all the modified files, and then M will give you the message, and she'll upload. Okay, since we changed our configuration, it had to do it twice because some things were changed. Anyway, cool. And so I love these little green boxes saying that all of our kind of little checks passed. We committed. So normally also in my pre-commit, I would have PyTest in there as well because I want to know that my code passes tests before I commit it. But again, normally you can also optionally just run PyTest before and then make one. But anyway, let us check out this GitHub repo and see what's up and set up our continuous integration. Oh, cool, things passed. Nice. So we have this initial commit. Setting up GitHub Actions is actually really trivial. So the first thing we do is go to Actions. So no, skip this instead of. Does it not recognize it's a Python project? Oh, we didn't push. No wonder. So once you push, GitHub Actions is intelligent. It'll look at the composition of your project, and it'll be able to tell what kind of actions to recommend to you. And so here we have pushed. Nice. We have all of our files here. Let's go to Actions. And as you can see, it's recommending a bunch of Python stuff. There's a few options. I would go with Python application right here. But for example, if you're working on a Python package, there's a package one. These are all really easy workflows to go with. Let's just set up a Python package. Hopefully you guys can see what I'm looking at on my screen. Cool. Let's zoom out a little bit. Okay, nice. So we are setting, basically to set up a GitHub action, there's a .github folder you create and workflows, and then you create this YAML file, which has information about what should be running. And basically we're specifying that the name of this action is Python application. We can change it to whatever we want. So I don't know, we can change it to build and run tests, for example. This will tell GitHub Actions when to actually trigger this. For example, when we push to the main branch or when we make a pull request to main, these actions will run. And then this is the actual job that'll run. So this is specifying that it's running on Ubuntu latest. First, it'll check out the repo. And so you'll notice this little v2 here. The reason is checkout v1 or the original checkout checked out the master branch, but we need a v2 because GitHub's new default is main. The next is setting up 3.9, but actually I'm using 3.8 locally. So let's just change that to use Python 3.8, and this will set up Python 3.8 locally. If you use the Python package version, that will set up a whole array of Python. So you can test across multiple versions. But again, for a local project, that's not really important. And here we can also install some dependencies. So I always upgrade pip and setup tools as soon as I install Python because that'll make sure you can build the packages correctly. And these lines basically installed PyTest and Flick8 as well as all your requirements. But since our PyTest and our PyFlix is actually already in our requirements, we don't need this line. Next, it'll actually lynch your code with Flick8, but we actually want PyFlix instead, so we can actually just do. So this is literally the commands it'll run in Bash, and so you can just change this to whatever you like. So for example, I want it to run PyFlix on my source directory. Same thing with PyTest, and so. I would not recommend running PyTest like this. I would instead recommend running PyTest via this -m. If you're interested in details why, you can definitely talk to me afterward. But we'll just do Python-n PyTest in the source, and then we'll also do the verbose output so we can debug things easily. So it was simple as that, just kind of setting up a few actions to run. We can just start this commit, make this commit here, and boom. And now we should notice that, okay, cool. Now we have this little yellow circle here that tells us that some checks are running. And so for example, here, you can take a look at the continuous integration actions that are running. So right now it's installing dependencies, just like you'd expect. And then if this succeeds, you'll get a green check mark. Otherwise you will get a red X. These can take some time to run. Normally you wouldn't be staring at it, I suppose, but for the sake of a demo, we will be staring at it. Oh, we forgot to change the name, but I promise it's linting with PyFlakes. So once again, just to emphasize, this is helpful because this makes sure the code that you committed is correct to some degree. Like you don't have weird misspellings, you don't have weird errors, you didn't forget to run tests. And even if you did forget to run tests, this will make sure that things work. And so if the tests pass, you won't get any notification, but if they fail, you will get an email with details about which ran, fail, and why it failed. Anyway, we will not actually wait for this. This is taking longer than I expected. How much longer? Yeah, it's doing some stuff. Let's actually skip along in our presentation, but just trust me that hopefully this will pass, and if this doesn't pass, it'll be embarrassing, but we will see. And we'll get a green little check mark here that shows that our continuous integration passed. And that now we basically have a setup where we're confident that our code is clean when it's going into our repo and it works. And oh, now it's running PyTest. Is it going to work? Oh no, it failed. Why did it fail? Okay, this is a good debugging opportunity to see what's going on. Okay, I think I know why. Hold on. So let's modify our action actually. So we can modify it straight on GitHub. So this is what you get when you get a failure. You get a little X, and then you can check out what's going on. I know why this failed, and this is a detail of PyTest actually. I would recommend being in your source directory when you run PyTest just because of the way Python imports work. Source, and then we can just do this directory here. If you have a package, if you make your little module a package, it's actually easier to run these tests, but I would just recommend running your test straight from your code directory. Hopefully this will work this time. Anyway, we won't wait to check, but I am more confident that this will work. Teachable moments. Nice. Cool. Let's power through. So now we'll briefly touch on version controlling notebooks. And if you have any experience working with notebooks, you know they are a pain to version control. And the reason is they're stored as human readable JSON. Actually, that's not the reason, but that is a fact. But the problem is the outputs are stored in binary. And so for example, if you have plots or any kind of graphics in your Jupyter notebook, Jupyter actually stores these as raw binary, and it stores it as hexadecimal text, so a hexadecimal representation of the binary. And so if you make a tiny change to a plot, or if you replot the same plot with like a different color, for example, this will lead to a completely different binary, which makes it super annoying to look at diffs between different commits to see what you changed, because a big portion of those changes will be these binaries. My recommendation would be to put as much of code as you can into these .py files, like I've been doing in my experiments, and just use Jupyter Notebooks for experimentation or running code or kind of iterating on ideas that you already have. And of course, you can put code into these Py files and then import them into Jupyter in a mini library if you're running Jupyter. Which I did not demonstrate in this because I was using Colab, but that's like kind of the typical workflow where you have a Jupyter instance running and you import files that are local. There are many tools out there that can help you version control notebooks more effectively. One tool is NBDev, which is an entire development system which is based around notebooks, which cleans them up and makes them version controllable. I don't find them particularly useful for my specific workflow, but you may find them useful for yours, so I definitely encourage you to explore. Cool, and now we are in the final stretch of the presentation, and we'll talk about kind of my favorite section, which is configuration. So in any machine learning or data science workflow, you are definitely trying different ideas and trying different things. You're trying different hyperparameters like learning rates or different optimizers, different kinds of models, and you don't want to have this hard-coded into your Python files. You want some separate entity which describes what kind of experiment you want to run, and then you want to run those specific experiments. And so configuration is how you do that. So again, you have an evolving set of hyperparameters and knobs that you tune over time that you want to change in order to kind of find the optimal model, algorithm, data, whatever it may be. But it's super easy to break backwards compatibility where you have some configuration that worked before and you have some results using that, and you change some stuff and you want to try something new, and all of a sudden your old config stops working because you added some new options to the new one or your code kind of changed. And so this is the most annoying, this is a very annoying thing in my opinion. And one way kind of people prevent this is by making these huge monolithic configs where all the options are in one big config file. And so you can keep adding things and kind of making sure old things don't break, but at the same time, they become huge and hard to understand what's going on and hard to actually modify and update in the future. Before showing you what I think is a good configuration looks like, we'll talk about some anti-patterns that are pretty common in researchy and data sciencey projects. The first one is really huge argparse or abseil argument lists. And so, for example, like they basically they define all of their options as command line arguments, and then just make a huge argparse list, which is argparse is Python's standard library solution for command line flags. This is hard to read. It couples your code with the configuration, and it makes them, which is kind of the opposite of what you wanted to do with configuration in the first place. Changing defaults is a pain because you have no idea what defaults you used before versus now. And so, either in experiments, you have to specify all the parameters, or you have to like keep the default set in stone for your entire project. It's very annoying. And it can be hard to understand if you're not familiar with code because you have this huge wall of arguments and you have no structure to them. You have no hierarchy. And so you have no idea what's going on. Another pattern is passing one monolithic config all over your code. And so what do I mean by this? So suppose you have some main code, you have a trainer class, which has your training loop. You have some model that's constructed inside of it, which is your model that you're using. And even within your model, you may have configuration for the layers, you may have configuration for submodules, etc. One strategy is to pass your config dictionary through all these functions. So every function has config inside its signature. And so this way you can add stuff, remove stuff from your config really easily. You can change stuff around. And as long as the specific part that each module needs is present in the config, it'll work. But this is awful for other reasons. Code is less modular. You can't just import a function and use it because you have to read the entire function, see what config contains, and then add those things to a config before you call the function. So really your code is just tied to the specific project and you will not be able to use it anywhere else. And you may be thinking like, well, I only want to use it for this project. But when you have things like learning rate schedules, things that you want to transfer over between projects, or even general functions, like for example, you use some kind of annealing in some schedule in some part of your code and you want to use it elsewhere in your project, you can't because you need this huge config object there too. And it's really hard to reason about what a functional action actually needs because you just get this huge config that has all the values in it, and you have to read the actual function to understand what values it needs, which makes it really hard to reason about what the code's doing. Another anti-pattern that's not really a different category, but it's more an orthogonal set is mutable configurations. I've seen a lot of cases where configurations are changed. I haven't seen a lot. I've only seen a couple because this is really hard to work with in practice. But seeing that configurations can change over time. So for example, you specify one thing in your config and then somewhere in your code, it mutates that value so that other parts of the code can use it. This makes it extremely hard to understand what's going on. And I would recommend keeping your configs frozen as soon as you import them into your code. My recommendation for what to use is a framework called Hydra, which is a framework for elegantly configuring your complex applications, which is a line from their GitHub repo. And essentially the key component is it makes composable configuration. So you no longer have redundancy and you can have multiple options for each little section of your code without making this huge config with many options. And this library has a lot of great properties as well. So for example, it gives you a command line interface to override arguments very easily. It allows you to sweep hyperparameters. So for example, if you have like a set of different learning rate schedules you want to try, it's easy to launch 3 different jobs using this tool. And there are also many other plugins like third-party options to do more things with these frameworks. And there's also a lot of other nice properties. So for example, it'll take care of logging for you. So you can use their built-in logger to get nice logging messages and output them to a file. It'll automatically create an experiment directory for you. So you can just save results to os.current directory and it'll be in the right place instead of making a new directory for each project, etc. It deals with a lot of stuff. It's pretty cool. So before I continue, I want to show you something called a dependency injection pattern. And this will as a way to transform your code so that it is easier to configure and less dependent on the configuration file. So for example, here we have a very simple example of where we have some dataset class. We have this example is taken straight from the Hydra documentation. We have some dataset class. We have some trainer, which is involved in training your model with some optimizer and dataset. And we have some configuration which specifies, okay, what kind of optimizer, what kind of dataset. Sorry, I don't show the optimizer code here. One common pattern is to literally pass the config into this function, and then you basically have a get optimizer function, which takes in another config and figures out what's going on and then returns an optimizer. A dataset which figures out what's going on, then it returns the appropriate dataset class. Because you can imagine you can have multiple optimizers, multiple datasets, etc. This is something that is very common and it seems kind of benign, but as your code grows, this will become harder and harder to reason about. What I would recommend instead using Hydra is doing something like this. So instead, you just specify, you pass in the optimizer and dataset directly. So here you pass in the configuration, you create the optimizer inside, but here you actually inject the dependencies. I'm doing air quotes right now. And so you actually pass in the exact things that you want. And then instead you just assign them in here. And everything else is the same, except in this configuration, you specify what class you actually wanted. So for example, if you have multiple optimizers, you may have myapp.optimizer, myapp.atom.optimizer, etc., etc. And I will stop moving my cursor so you can see the code at the bottom left of the screen here, which is this instantiate function. And so essentially, it takes in this trainer config, and it can recursively instantiate, okay, so this trainer wants an optimizer, and the target is myapp.optimizer. So it will construct this with these arguments. Same thing for dataset. You can see the dataset, the target is myapp.dataset, which is this class here, and it's constructed with these arguments. And this allows you to keep your code really simple. It's just a one-liner here. And all the information about how this thing, what values this thing accepts is inside the config. You don't have to be confused about any global dependencies or what's going on. It minimizes the branching logic inside the code and just makes everything a lot simpler to work with. Cool. So now, it says logging with demo. It's logging with Hydra. It is not logging with Hydra. It is just Hydra. So here we will talk about how we can use Hydra to configure our project that we've been working with. And this is not going to be a in-depth tutorial about how Hydra works. Actually, I provided a link in the syllabus, which has a really good tutorial on the Hydra website about the basics of getting it set up and getting it working. But I think I would like to supplement their documentation with this example, which is more like a smallish project with some realistic configuration for machine learning and examples of how you can use it. So let's take a look at, cool. So the overall project structure, once again, just to kind of give you a refresher, we have here our source directory, which has all of our development files. We have our configuration in here, and we have all of our files here. So for example, our data is in here, and our main is what actually runs the code. And so if you can see our main file here, we have our main function, which is decorated with this Hydra decorator called hydra.main. And we specify what the configuration name is and what the path is. And we'll kind of show you what this looks like a little bit later. And throughout this code, we basically use Hydra. Let me show you actually show you the config first before we dive into that. So here's that directory I was talking about, which has all the configuration options. This is our main configuration. We have a lot of information about the experiments we're running. So for example, we have the seed here, we have the number of steps, we have the batch size, etc., etc. We have like an image generator we want to instantiate, for example, which is like this class from TensorFlow. And it'll instantiate this for us, and it has some various hyperparameters. This takes in an argument called a preprocessing function, and we can, again, recursively instantiate it. So we have this function called getDataEraser. It'll call this and get the right thing for us. And so these defaults here, so previously, for example, we could have had an entry called epsilon schedule, and then we could have some information here. But instead, we refactor these out into different files, and I'll show you how those look actually afterward. So these defaults are basically what will be inserted into our config normally, but I will show you what they actually look like. And so here we have all these different options, and these are various things that we wanted our code to try out. And so for example, for our schedule for the learning rate, we may have two different schedules, like a constant schedule and this schedule called a one cycle. And so if we look at the constant schedule, the target, this will instantiate this constant learning rate schedule from this library called optax, and then it takes in a value of 0.01. Or for example, we can have a one cycle rate, which is our own custom implementation from the schedules file. We can have a maximum, we specify 2 arguments for it. Here I'm using something called interpolation. And so this is saying that, okay, somewhere else in the config, I defined this num steps, just grab that value for me. And it grabs it from right here. So in terms of actually using this, this is how this looks. So let me see if I can actually split my screen. I don't want to make the text too small. Yep, let's actually, I'm going to zoom out a bit so you can see a little bit more about what's going on, but please let me know if this is too small. Or I guess you can, it's a video. Anyway, so here, for example, we have our model and we instantiated our model using this config, so fully connected. So let's look at how that looks. And so we have fully connected here. The target is models.fully connected, and we specify the layer sizes. So we can see that models.fully connected over here. We have this fully connected class here, and it takes in the number of classes and the layer sizes. And we can see here when we instantiate, the layer classes is already provided by this entry in the config, and we can optionally also add a number of classes. It's not specified. Again, these little minute details are in the documentation, but I just want to show you the high level structure. So this allows us to specify what kind of model we want really easily in the config. We can also, instantiate different kinds of schedules. So for example, it's epsilon schedule. What is it calling here? Let's take a look. For example, exponential, it's calling schedules.exponential decay. Let's take a look at that. So we have this exponential decay here, which is returning this schedule function here. And so when you actually call hydra.call this function, which is actually the same as instantiate, but anyway, it'll call this function with the arguments that are given in the config, and this will ultimately return a function here, which we can use in our schedule. Again, the details are not too important, but I just want to show you how much more composable this is than other solutions, because you're no longer passing these massive configs. Like you see the config nowhere else in the code except in the main file. You can easily specify options here. So for example, I can run Python main.py, and then I can, specify, for example, eval frequency equals 10 instead of 2000. And super easy to override these options. I won't actually run this, it'll take a long time. You can also specify the defaults. For example, LR schedule, instead of the one cycle, I can actually specify it to be constant, and it'll find that config and run it for me. Or within an LR schedule, maybe I want a particular value. So for the one cycle schedule, maybe I want the max LR to equal 0.1 instead of 0.01. So you can override these easily via the command line. You can change these in this config file here. And as you saw in my testing directory, it makes it easy to test as well, just by importing in the configs. And yeah. So again, this is a super high level overview of what this can do. I would encourage you to look at this code more closely and also follow the tutorial I link in the syllabus, because that will definitely clear up how to use this more effectively. But I just wanted to show you the high level structure here. Cool. So that sums up the workshop. So what was our goal? Our goal was to invest some time in the beginning of a project to speed up progress later in the project. And how do we achieve this? We covered how to use Python environments to isolate our dependencies, and so other people can run our code, or we can run our code in the future without worrying about this whole soup of dependencies and wasting time managing conflicts. We talked about testing, and we talked about the fact that testing doesn't have to take up a lot of time. It can literally be copy and pasting the example you use to actually develop the new research idea or implement the new feature or whatnot. This is not like software engineering. You don't have to go through all the edge cases, but you should have something to make sure things work the way they did before. We talked about static analysis, which is a way to verify that your code, doesn't have any glaring mistakes before it's run, which is super helpful because, I'll say this again, nothing is more annoying than running code for a day and then it failing at the very end. We got some tricks for version control. We set up pre-commit and we set up continuous integration, just very, very basic versions of those, so that we can just verify our code is clean, and we can verify that our code is working when we push it to GitHub. And finally, we did a high-level overview of some configuration of how we can configure our projects to not follow these anti-patterns and instead use a framework that allows us to make these composable configurations where we can ensure things continue running the way they did in the past and easily build up on new ideas. So here are some resources. There are more resources in the syllabus, but these are, I think, the minimum that you should check out. The first is a UWaterloo Data Science Club Linktree. We have a YouTube channel with a bunch of past workshops, and we host workshops like these all the time. So I'd highly recommend joining and being a part of the community because it's a great way to learn some more. The next is the Hydra tutorial. This is like the first thing you see on the site, so I really didn't even need to include this link. I tried to avoid links that are just kind of the first thing that appears on Google because when you Google, you will find those. But this is kind of important because I think it's an excellent tutorial kind of showing how you can use Hydra. And yeah, thanks for listening to this recorded version of the Hack the North workshop, and I hope you enjoyed.